Good afternoon, everybody. Thank you once again for another set of EI Live for K-12 students and educators. This is being brought to you by the Earth Institute at Columbia University. My name is Cassie, and I'm the Director of the Office of Education and Outreach, and one of my big areas of responsibility is actually bringing our scientific research to different audiences, including K-12 students and educators. So for those of you joining us for the first time or aren't familiar with the Earth Institute, our core mission is to foster a greater understanding of the science behind sustainability and the climate crisis and what we as global citizens can do. Experts that make up the Earth Institute are quite diverse and include earth scientists, economists, business and policy experts, and specialists in public health and law. The Institute is made up of more than 24 research centers and several hundred people who work across many different disciplines at Columbia University. What we're hoping to do with these particular sessions is to introduce you to the interdisciplinary work of our experts. And we'll have these sessions until the end of June for K-12 students and educators. And we'll have a couple of sessions planned for the summer as well. So today we're going to hear from Josh Russell, a PhD candidate at Lamont Doherty Earth Observatory at Columbia. He's going to be introducing us to the world of data sonification, which is transforming data into sound. And he'll also be explaining how scientists use this process to understand the natural world around us. So this is actually part 2 of a series that Josh has done for us. And if you didn't catch a session on Monday where he showed us how he was using Python programming to turn seismic data into a visual story, that recording is now available. And you can find that either on the EI Live website or through the Earth Institute's YouTube channel. If you're having any issues, just email me directly and I'm happy to send you the recording. So just a quick reminder to use the chat box just to the right of this video to ask and answer questions. So Josh will likely ask our participants some questions throughout. And if at any point you do have a question, feel free to type it right into the chat box and we'll monitor it throughout the talk and we'll make sure we get all your questions answered. So you can also feel free to email me directly if you don't want to use the chat box. Once the session is done, we'll share a link with everybody who's registered for the event so that you can watch the recording later on. And we do make the video private for a couple of days while we edit it. So keep an eye out for an email from me for when it's posted to YouTube and available for you to watch. And let me know if you're having any technical difficulties via email. So without further ado, I'm going to hand it over to Josh.
Okay, so today I'm going to be talking to you guys about sonification of data. So taking data and turning it into sound and how we can sort of use this and the fact that as humans, we're really good at picking out patterns both with our eyes, but also with our ears to try and learn something about the Earth. And I will suggest that people try and grab a pair of headphones if they can, because some of these sounds just kind of come through better that way than they do through your computer speakers. Okay. So before I kind of get started, I sort of want to acknowledge the Seismic Sound Lab at Lamont. And it's run by Ben Holtzman, who is a research professor at Lamont. And he's been doing this for quite a long time, taking data, and in particular, he started with seismic data and turning it into sound. So on the left is sort of their first exhibit in 2006, which I was not a part of. I was like 13 at that time. So, and on the right is sort of what it's grown into. And in particular, their very successful Seismodome exhibit at the planetarium. And the most recent one was in 2016, but hopefully they'll come back with those at some point. And if you want to kind of listen more about that and hear more about that, there are some links on the Sound Lab website, which is also on the webpage that I think Cassie shared with everybody in the resources section. So I played this video last time, and I wanted to play it again because we're actually going to turn back to the Tohoku earthquake in this session. So last session, we talked about where earthquakes happen and where they kind of occur on Earth. And in this one, we're really going to focus on the waves that, that are emitted from earthquakes. So I'll just play that again. And this is what you're actually hearing in this video is seismograms that are measuring ground motion actually turned into sound. And that's what this whole presentation is going to be about. We're going to go through how that's done, and we're going to listen to some of our own sounds from this earthquake. So I'll just play it one more time. And the visual part is the actual wave field from the 9.1 generated using a computer. So these are computer generated seismograms, but the way that it's actually then turned into sound is all the same. So what you're seeing are a bunch of different types of waves, body waves, surface waves. We're going to talk about some of these later and kind of go into more detail, but that's kind of just to give you a flavor of what, the sorts of things that you can kind of do with sonification. And this video, so that video, we're looking at the Earth kind of from the outside looking down on it, but in the Seismodome at the planetarium, you're actually inside the Earth, and all the sound is kind of like happening around you. So you'll feel the waves kind of go past you and then hear them bouncing around. It's very cool. So the whole goal of sonification, or one of the, I guess, kind of the challenge of it, is taking a process that happens at a really long time scale or a really low frequency. And so in particular, seismic data happens in sort of the blue region of this frequency scale, and turn that into something that we can actually hear. So the red part is the kind of audible range of human hearing. And on the bottom is a seismogram with kind of the audio time on the bottom axis and like in the true seismic time on the top axis. And so you can see in this case, you would take 300 seconds of time and crush it down into 2 seconds. And in the case of the Tohoku earthquake that we're going to get to, the example, we actually take 7 hours of data and shove it down into just a few seconds. Yeah, so it really is just compressing the kind of the data. You keep all the information there, but you're just compressing it. And so it allows you to really get a sense for maybe what's a really big data set, and crushing all that into a few seconds and seeing what you can gather at kind of the broad scale. So some of the learning goals, again, kind of similar to last time, I've kind of broken it up into 2 parts. So the first part is we're going to focus on waves and kind of exploring that a little bit, exploring waves a little bit with Python. And we're going to try again, for those of you who were here last time, it didn't work so well, but I've tested it out again this time and it seems to be working. We're going to try using these Trinket. It's called trinket.io, and it allows you to run Python in your web browser. So we're going to try playing with that a little bit and make our own waves. And on the seismology side of things, I hope that people will kind of go away from this having learned something new about seismology and about how waves work and how waves are generated from earthquakes and what that looks like. And then at the end, again, for those of you who were here last time, you'll remember that we looked at seismic noise in New York City. Well, I stayed up fairly late last night trying to sonify that and turning that into sound. So we'll get to listen to that at the end. So here we go. So first, we're gonna just review sound waves again. So I actually showed this last time, but the basic sound, the most simple sound wave that sort of occurs is the sine wave, and it has an amplitude that's just the height of the peaks, and it has dips, those are called troughs, and then it's got every wave has a characteristic wavelength, so just the length from one peak to another peak, or one trough to another trough. And that's related directly to the frequency. So the higher the frequency, the shorter the wavelength. I think a lot of people kind of have that intuition already. And so we're going to add a little bit to that, and we're going to kind of explore that in a little more detail, because I think it's useful to understand kind of the wave physics and yeah, sort of the conceptual understanding of the wave before we really dive into things. So I am going to go, and you guys can as well if you want to try to. Can actually go now to this website. So it's the one I think that Cassie shared, jbrussell.github.io/eilive2020, and then it's part 2 sonification. So I already have that opened.
I'll also share this in the chat with our participants, just in case they don't have it.
Are you able to see a browser right now? I think the answer might be no.
No, it's still
okay.
your keynote.
Great. Not great, but I'm gonna fix that. Okay. Now you should be able to see a browser.
Yep, perfect.
Okay, great. So, right, so this is the EI Live page, and you can either click part 2, or you can go over here and click turning sounds into data. And so hopefully things will load up. It's been a bit slow because I've added a lot of stuff to it. And there are probably a lot of people going to it at the same time. So let me take a second. But what you should see is a little display like this. And so this is code that was generated using a library called Bokeh, which will look familiar to people that were here last week, or not last week, on Monday. And if you want to see where the code is, you can just click here, view code, and it takes you to the Python notebook. But we're not going to do that. We're just going to focus on this window. So there's an equation up here. This is the equation for a wave. So this is the equation of this wave here. And so you can change all these parameters and see kind of what they do to the wave. So this is the amplitude. So that's A above. This is frequency. That's F. And so as you increase frequency, you just increase the number of cycles within a given time window, or window of X. Phase is just where the wave starts at 0, at X equals 0. And offset is shifting the whole thing up and down. And so in the case of sonification, we don't like having an offset. So what actually is going to happen when we sonify this data is the positive values will be your speaker moving up, and then the negative values are your speaker moving down. And so you want everything to kind of pass through 0, or else you're not going to get any sound. So if you have everything way up here, it's just going to be, your speaker head is going to be up against the wall and you won't hear anything. So that is kind of the basic, yeah, just to give you kind of a more intuitive understanding of what these different terms are for the sine wave. And next, we're actually going to try, well, actually, let me go back. I think I have something else I wanted to say before I do this. Right, so there are other types of waves. Let me go back to full screen. Right, so there are lots of other types of waves. We just talked about the sine wave, and that's kind of the simplest one, and it's also the one that sounds the nicest. But there are also other types of waves that have all different characteristics. The square wave, really common, triangle, sawtooth. But if you were to actually listen to these, you can go on YouTube and find them probably. The sine wave is kind of the pure tone, and then all these other wave types have a very different sound to your ear. So a lot of like electronic music, for example, uses sawtooth because it has kind of a robotic character to it. And so we'll actually explore a little bit the difference between a sine wave and a square wave, but I don't want to hurt your ears too badly because it sounds pretty, it's like kind of nails on a chalkboard type thing. So, so the other thing we're going to try exploring with the trinkets are beats. So when you have two waves that are interfering with each other and they're really close in frequency, actually, if you just have two waves and they're close in frequency and you add them together, that's kind of the simpler way to think about it. You get what is called a beat. And so this little image here is showing two waves, a red and a blue, and they're both at a single frequency. They're just kind of overlaid on each other. And then underneath is what happens if you actually add them together. And you see a nice beat. And the really interesting thing about beats is that once you get a certain frequency distance away from one wave away from the other wave in terms of frequency, you sort of lose the beat. And so, yeah, we'll kind of explore that hopefully with the trinket a little more. So let's see. All right, so it's actually the same page. Just scrolled down a little bit. So this is the trinket, and you can see it's already run, and I'm gonna try opening it in full screen because I think it'll be easier to see. Right, so on the left, on this side, you have all the code. And on this side, you have the window with the plots that you can generate with the code. And then this button up here is what you click to run the code. So you can click it, hopefully it'll run. Yeah. So what this is actually doing is up here in this little box called make changes, I've defined parameters for two waves, wave number 1 and wave number 2. And these F, A, B, and C are the same parameters from that equation. So it's the frequency, the amplitude, offset, and phase. And then down here is the number of cycles, and that just controls how many cycles are actually plotted over on the right. But kind of the interesting thing, so we ran it with a frequency of 200 hertz and a frequency of 300 hertz. And so you can see when this one's the 200 hertz and the bottom one's the 300 hertz. And this is when you add them together, you get this weird kind of strange looking thing. But you can, yeah, maybe you guys are already doing it right now. You can change the frequencies and see what kind of happens. So for example, if you wanted to do 210 hertz. So basically moving the frequencies closer together, like I said, kind of helps create a beat, because you don't really get a beat in this one. Yeah, there we go. So, right, you get, and if you were to lay this wave and this wave on top of one another, actually we can do that very quickly. So down here is the plotting, and so we can actually plot now the Y1 and Y2 on top of each other. They'll both plot right here, I think. Everything works correctly. Yeah, so you can kind of see what we were just talking about. So in this part, you have waves. The waves are almost perfectly overlapping. And then as you get further away from that point, so that's where you've got like the maximum in the beat. And as you get further away from that point, they're destructively interfering is what we call it. When the peaks and the troughs are kind of opposite, we call it out of phase from one another, then you get a 0. And so, yeah, you can sort of play with that and you'll find that as you get further and further away, the frequency of the beat actually increases. And so the frequency of the beat is the difference between the two. I think it's just the difference between the two frequencies. Anyway, we probably have spent too much time on this. As you can tell, it's I had a lot of fun with it. So that's just kind of to give you an example and just sort of get a feel for what these waves look like and the properties of them. And so next we're gonna listen to some sine waves. And I've chosen the same frequencies that we were just playing with above. And so what these videos are, I'm actually gonna start with this one. What these videos are showing 2-second increments of sound, or what they're gonna show is 2-second increments of sound. So this might look like a blue blob or blue box, but if you zoom in, it's got all the, it's basically a sine wave. It's a little jagged because I didn't, yeah, don't worry about that. But what's gonna happen is when you push play, everything's gonna play, and you'll first hear this one, which is the 200 hertz, then you'll hear the 300 hertz, and then you'll hear the sum of the two. So. Sorry, I should have warned you so I didn't blow anyone's eardrums out. Yeah, so I'll play that again and just listen to, in particular, what the, yeah, whether or not, you can think about whether or not you hear a beat. Okay. Now we're gonna do, you can already see this one has really clear beats, but the 200 hertz and the 210 hertz. So I'll play it one more time. Okay, so I think, yeah, maybe I can actually stop here and hopefully people could hear those, and just, I guess the question is what is the difference, sort of what did you hear different between the two, and was there, yeah, is it sort of what you expected? I know it's a very broad question to ask, but, or any questions you have up to this point. I've kind of gone through a lot already, so.
Thanks, Josh. Let's give our viewers just a quick chance to maybe listen and re-listen, and then have a chance to type into that chat box. So I have a question for you. I mean, this is, what is the, for the Seismic Sound Lab, I mean, you work closely with Ben. What does a sort of typical day look like? Because that is, you know, this is some really cool stuff, and this is definitely a very unique project that's part of Lamont and part of Columbia. You know, we haven't really thought much, or I personally hadn't thought too much about, you know, seismic sounds or seismic sounds. And, you know, we know about earthquakes, we know they're sort of about how destructive they can be, but since I met Ben, this is kind of my first introduction into how scientists kind of turn data into sounds. So, you know, I'm curious what a typical day looks like. And, you know, he works with, I believe, Jason Cantor? I can't remember what his last name is at NYU. It's a sound, he works with a lot of sound engineers, which is super cool. So I'm just curious if you could talk about, you know, the lab and what a typical day might look like for you guys.
Yeah, so I sort of have been peripherally helping with the Sound Lab stuff during my PhD, so it's not my primary focus. But yeah, Ben has worked for a long time on these sorts of things, and so he actually has, I think his main research is not necessarily focused on the sonification at the moment, but he has, for example, published papers on sound and data. So he did a study where he was looking at geothermal fields, the geysers geothermal fields in California, and listening to the earthquakes, and actually was able to pick out 3 different types of earthquakes based on how they sound that other people had missed. And I can post a link to a write-up about that or something. Yeah, he also teaches a class that at Columbia that's cross-listed with the computer music school. So it's computer music majors and earth science majors kind of all together in a classroom, and you work on a project with someone and you're kind of like bouncing ideas off of each other. And he's had a lot of really cool videos and things come out of that. But the main focus of the Sound Lab is really to try and help the general public sort of connect with the earth sciences in a way that they maybe haven't previously.
Great, thank you. Yeah. So in response to the question, we actually got a question from one of the viewers. So she's asking, why did the sound separate during this current view? It sounds like it looks, but she's not quite sure why it's happened here and not in the previous view.
Yeah, so so there are actually, I apologize for not explaining what this bottom thing is. So the top one is time on the x-axis and the amplitude of the wave on the y-axis, and the bottom one is showing the time, and then it's showing the frequency of the wave at that moment in time. So the light colors are higher power, and so this is saying during this time there's a high powered signal at 200 hertz. And so I think maybe the separation that they were referring to possibly is this separation. So maybe, so there's the 200 hertz signal and then the 300 hertz signal, and then there's the really clear, you really clearly hear 2 separate tones. You don't hear the beating like you did in the other one. And that's just because they're too far apart from one another. And so the frequency, the beat frequency is so high that you sort of lose it, and your brain is not able to process that. And so in this one, they're much closer together, right? And then even if you look at the overlapping one, the 2 lines are very close to one another, and that allows your brain to kind of hear that beat phenomena. I guess I'm not a physiologist, so the whole the whole physiology of like how the ear is hearing that stuff is pretty cool, but I don't know a whole lot about it.
That was great. Thank you for clarifying that.
Cool. Maybe we'll move on then.
Yeah.
So I think I will let people explore this one on their own because it actually is very loud. I would warn you ahead of time, but basically on the left side is a sine wave and on the right side is a box wave of the same, they have the same shape, but one's a box wave, the other one's a sine wave. So you can explore that on your own if you would like to. Okay, so, oh, and I should mention, oh, never mind. That's this one. So on this one, I wanted to just show what happens if you change the kind of shape of the wave as you go. So this is a single tone, but you're sort of changing the wave. And actually this one starts to look a lot like a seismogram. You have the waves, strong waves arriving, and then they sort of decrease as you go further in time. So this is kind of a, yeah, very rudimentary earthquake, I guess you could think of it. So you can play it in 3 different time chunks. So the first one is 2 seconds long. This one is 5 seconds long. And the next one is 8 seconds long. I won't play the whole thing, but. Okay, so I just wanted to stop here and ask, yeah, so is that, well, I should have. Yeah, so I guess the main thing you can hear is that as you go to longer and longer duration, your frequency gets lower and lower, and that's because you're sort of expanding the wave for the same number of wave cycles in that chunk of time. You're sort of making the wavelength longer and longer and longer, if that makes sense. And what it's showing, and you can actually see that in the spectrogram on the bottom. So as you go from 2 seconds to 5 seconds, the frequency goes from 400 hertz to 200 hertz. And you can see the amplitude of the signal, the amplitude, sort of the power of the signal. It's actually a bit hard to see, but it starts out weaker and then it gets stronger and then goes weaker again. And that's just because the wave is kind of changing from a strong power here and tapering down to 0. It's a little hard to see that, but okay. So I really just wanted to run through those like very simple examples just to show you kind of what, when you look at a waveform, you can already kind of start to tell what it's going to sound like, but there's a lot of detail in the sounds that you don't necessarily pick up just from looking at the seismogram or the waveform. Okay. So we're going to talk about seismic waves now. So I showed this video last time, but I'll show it again because it's a really good demonstration of how seismograms kind of work, or how seismograms are measured. So the star is going to denote an earthquake, and the triangle is a seismometer. And up here, you'll see this blue dot sort of trace this out with time. So I'll stop talking and just play it. So you can see all the waves coming out from the star, the earthquake, and then you see the first wave hits and you get the little spike here. And then later you have the much larger waves. And so those are called surface waves, and the ones that come later, and they're much bigger in amplitude, you can see, and those are the really kind of destructive ones. And this first arriving one and the ones right after that are body waves, and those actually travel down into the earth. The surface waves are confined to the top layer of the earth. And so this is kind of what a typical seismogram sort of looks like. You have the first arriving wave, that's the P wave, and then you have an S wave, and then a surface wave back here. Okay, so, and you can tell like this seismogram up here looks like kind of like some of the stuff we were just looking at, but way more complicated, and there's way more going on in these than there are in a simple sine wave, but we can turn them into sound just the same way. Whoops, too far. So this is an image showing all of the seismometers in the International Registry of Seismograph Station database. And it's not all they're not all out right now measuring ground motion, but it's just all that have been out at least at one point from, I think, back to the 1960s. So there's a ton of data, a ton of seismograms to go through, tons of data. And actually a lot of these stations were deployed in order to monitor for nuclear testing with the Nuclear Test Ban Treaty back in the 70s. And today that's still going on. We're still monitoring for, well, I'm not personally, but there are people that are using seismic data to monitor for nuclear explosions. But basically this is just to show there's tons of data. So when an earthquake happens in Japan, for example, it's going to be picked up all over the world. And all that data is available for people to look at. So this is kind of just a schematic of what we looked at before, but just to sort of more directly tie the waves into the seismograms that we measure. So it's showing you an earthquake at the top of the earth, and then at the top of the picture, and then the waves kind of travel down through. There are some that go through the mantle, the red part of the earth in this photo. some pass all the way straight through the middle, pass through the core, and come out at the end. There are some, if I had my cursor, I just go out for a second to show you, there's actually some weird stuff happens here with the waves refracting, and that's because the outer core is liquid. And that's actually how we know, one of the main ways we know there's a liquid outer core. And so seismologists are really used to looking at this thing on the right, which is called a record section, which has time on the x-axis and distance away from the earthquake on the y-axis. And it's a very reproducible thing. Every earthquake has kind of the Earth's fingerprint recorded in these record sections. And we can use that to understand things about the interior of the Earth. Okay, so we're gonna move on to the Tohoku earthquake. And before we actually sonify it, I thought I would just spend a little time talking about it because it was a very significant earthquake. It was one of the largest magnitude that's been recorded in our kind of current day catalogs. It's the 4th largest overall, and it's the largest one that we've seen in Japan. And it produced a tsunami that killed a lot of people and left a lot of people homeless, which is unfortunate with these big earthquakes, and damaged a lot of infrastructure. And I saw somewhere quoted at something like 235 billion, and it's quoted as the most costly earthquake in, natural disaster in history. And the Earth moved a lot during that event. The mainland of Japan shifted east about 2.5 meters or about 8 feet, sort of lunged towards the ocean. And it actually, someone did a study, I actually don't have the citation for it, but there was an estimate that it actually changed the Earth's rotational speed a little bit because when this fault ruptured and kind of the solid Earth kind of reorganized itself beneath the fault, that actually slightly changed the center of mass of the Earth, just very tiny amount. And that's enough to kind of create a little wobble in the Earth's rotation. And so the estimate was 1.8 microseconds per day of time that has, I think it was that the days are actually shorter by 1.8 microseconds, which is insignificant for us, but I thought it was interesting. So I wanted to show you what some of the seismic data that was actually recorded from that earthquake across the United States. So this video is on the Seismic Sound Lab website, and it was made by Martin. Oh gosh, I'm blanking on his last name. And he, anyway, this video is will show the ground motion from both Haiti and Tohoku, but I think we may skip Haiti just for the sake of time. And so these white dots are showing seismic instruments, and you can see them sort of marching across the US. So this was a big experiment called Earthscope that took place from about 2004 and is actually still going today. All the seismometers are up in Alaska right now. And so it's been a massive undertaking, and they sort of just marched the seismometers across the United States and were able to measure some really cool things. So the sonification, or the sort of visual aspect, will go like this. You've got waves coming across, and these little circles will move up and down, red and blue for up and down. And so I'm actually gonna fast forward a little bit so now we're gonna watch the waves from the Tohoku earthquake come in across this. So I'll just stop it. And this is sonified. We're gonna do this sonification. And you can actually see something interesting which we'll talk about in later as well. I don't know if you noticed that, but the waves actually start going the other direction. And I can't remember if Genevieve showed this video in her session, but I wanted to ask if anybody knows, if anybody can guess kind of why that would be. So you can see the waves. Let me just play it one more time. So you can see the waves going across sort of from northwest to southeast. And those are the surface waves, those really big ones that go across. And if you have your headphones in, you can like really hear this low frequency. And then right about now, you see the waves going the other direction. And I just kind of wanted to ask people what they thought that could be.
Okay, thanks, Josh. Let's give our viewers a chance. If you wouldn't mind replaying the video again.
Yeah, sure.
And then I've written the question out in the chat box, and for folks to see. It's, can anyone guess as to why the waves change directions?
Yeah, exactly. And I guess while we wait, we can watch the Haiti one.
Okay, great.
And we'll see evidence of this later with some of the data we'll look at ourselves. So, it happens also with the Haiti earthquake, but it wasn't quite as clear.
So we have a couple of responses. So coming from the other side of the Earth, and perhaps they're reflecting back.
That's a really good thought. Yeah, that's very, very close. And there are waves that do that. There are waves that go all the way down and pass through the core, for example, and then bounce back. But that, in this case, that's not actually what's going on. Okay, so I'll actually let me see if that's the next. Oh, okay, actually, yeah. So the next thing is that. So I'll just talk about it very quickly. So now, so basically what it is the waves going the other way around the Earth. So for example, the first thing that you see, the really big wave that comes across is called a Rayleigh wave, or it's one of those surface waves that I was talking about earlier. Sorry, and it's labeled R1. It's the first arriving Rayleigh wave, and then at the same time, you also have R2, which is the Rayleigh wave that goes around the long way and comes around the other direction from the earthquake. So it really is the same waves that are generated from the earthquake. They're just taking a different path to get to the station, to the seismometer. And then R3 is, again, it's the same thing. It just goes around kind of another time. And so they'll go around and around and around. And we'll see some of that later. And on the left is showing the record section again with time and distance, but this time it's on its side. So time is on the y-axis, the vertical axis. Anyway. So, okay. I'm gonna pause here, and we're actually gonna go back to the website, and we're gonna go to the TOHOKU section. Sorry. So this time we're going to look at data from 3 stations. So one of the stations is really close to the epicenter. Yeah, so the first one is MAJO. They just have these 4-letter names from Japan. And then there's one also in Missouri. So it's kind of the in-between distance. And then there's one almost on the other side of the Earth. It's almost antipode, is what we call it, to the earthquake. And that's in South America. So yeah, we're going to kind of explore what the sounds, how the sounds are different from these 3 locations. And before we do that, we're going to look at some of the background noise. So it's important to know kind of what you're listening to when there's not an earthquake to really understand kind of what the novelty is of an earthquake happening. So, so here I've just sonified some data from that station in Missouri, P39, and I've done it at two different durations. So you can kind of hear the difference in the frequency pitch. If you don't like the high frequency, you can try the lower frequency. And I'll just play it. Let me turn the volume down a little bit. I should turn it down a little more. Yeah, so it just sounds kind of like white noise a little bit. But I don't know if you guys hear it, but you can almost hear the frequency kind of increase a little bit at the end. Just play it again. Yeah, you may have to listen to it a couple times to actually catch that. Let me try the longer duration. Sorry, I don't want to hurt your ears. So I think that one you can hear a little bit better. The sound actually changes a little bit through time. And that is, I actually don't know what that is from. I just randomly took this data at the same time of day that the Tohoku earthquake happened, but on a different day, a few weeks before the earthquake. And I actually don't know what that is, but I think and it sort of aligns with when daylight hours are. So I think it might be people moving around near the station or something, or maybe it's a temperature related signal when the sun comes out or something. I don't know what that is. I wasn't expecting to really hear much because again, if you just look at the data, it kind of just looks like nothing, but there actually is something sort of interesting going on. There also, you may notice, this isn't completely, for a given time, there actually is some structure in this. And people have been studying that for a long time. They sort of call it just the Earth's hum, or kind of the Earth's background level. And what it's attributed to, so there's this kind of broad, bright signal that in terms of the sound, it's like 400 to 800 hertz or so. And in frequency, that's like 20 seconds, 10 seconds to 20, or 0.1 to 0.2. And that is actually the ocean microseism. So it's the ocean waves crashing into the coastlines of the continent, and that produces waves that then travel across the continent. So you can sort of think about that for a second, how that can work. But basically, you've got waves crashing against the coastlines all day, every day, and that actually produces seismic waves that we can see in Missouri. And there's another one down here, and it's a similar process, but it has approximately double the frequency, so it's called the secondary microseism. So there actually is some interesting stuff even in kind of the background noise. Okay, so we're gonna listen to data from the actual earthquake now at the different stations. And I think I'll just go through, and play them, and we can just listen together kind of what they sound like. So I'm going to start with the furthest one away, and then the intermediate distance, and then the one that's really close to the earthquake. So this is the one that's far away. I'll play it again. And you may not be able to hear that if you don't have headphones in, because it's a much lower frequency, it's a pretty low frequency signal that the computer speakers, or at least my computer speakers, don't pick up very well. So, and the second one is the one in Missouri. So I don't know, you may have to listen to them back to back more closely to hear the difference, but there is a difference in them. And then finally, the last one, it sounds very different. Play it one more time. So you can hear the one that is closest to the earthquake has a huge signal because it's right close to it. And I don't know, to me, it sounds almost like a gunshot or something, or someone breaking glass or something like that. And you can see there's actually another one right afterwards, so you can hear both of those. And that's a magnitude 7.8, I think, aftershock that occurred about half an hour after the main shock. And you can also, again, you can see this thing back here, which actually is the Rayleigh wave that's then come back around again, like we were kind of seeing before. So this one would be the one that's traveling sort of the other direction. And you can't really tell from just looking at the waveform, but you can see in the frequency spectrogram, there are all these vertical lines going through. And I just wanted to ask people what they thought those are. If anybody has an idea what those vertical lines are. You can kind of hear them because they show up in the audio, they sound like just pops, vertical streaks like that in the spectrogram. And I kind of wanted to hear what people thought those were.
Okay, great. While we wait for some responses there, we had a question come up about the waves when they travel around the Earth. Do they create interference when they meet or overlap?
Yeah, so they do. It's not enough to, it doesn't, it doesn't like hurt anybody. It's not like they're gonna focus on the other side of the Earth and like damage things. But they do that. They focus, so when an earthquake happens on one side of the Earth, the complete opposite side, the waves kind of go around and like focus on the other end. So that's a great thought. So they do that. And there actually have been studies that have argued some of the volcanism on planet Earth in the early days could have been from like a meteor impact hitting one side of the Earth, and not actually the meteor impact being the thing that caused the volcanism, but the waves focusing on the other side from such a huge event like that. So that's a really cool, that was a great question.
Great, yeah, definitely a great question. I would suggest maybe moving on and then giving people a chance to maybe take a guess about what the vertical lines are, and then we can always come back to it.
Yeah, sure. Yeah, absolutely. So there's not too much else. I just wanted to show, since we did talk about it last time and maybe some people are interested in it. So last time we talked a little bit about the noise in New York City measured at a seismometer in Central Park, and that it has actually, the noise levels have decreased as people have been staying inside more and businesses have been shutting down. And there's this so let me go back to the presentation really quickly. So there's this signal that looks like this, and you have all these spikes. So those are the daily signal. People got that last time. And as you cross the quarantine, the stay-at-home order in New York City, the sound level, the noise level goes down, and it's just kind of been at this low level for the last few weeks to months. So in order to actually sonify that, we want it, so you can see right now the y-axis is 0 to 2, but we want it to be passing through 0 so your speakers can hear it. So what I've done is just subtracted off the daily average, and so this is what it looks like. So this thing on the right is what we're actually sonifying, and it's only sampled every hour, so it's a really hard thing to hear, so I had to speed it up a lot in order to actually hear it. And sorry, should have warned you. So I'm just going to play it really quickly, and I'll do this one, and then I'll do the 4-second one just to compare. So it has a, you can hear, yeah, so one thing you can hear, I think, is beating, and that's kind of the weekly beats, I think. So these little clusters, each of these spikes is basically a day. And so it's 5 days spike, and then it gets smaller, that's the weekend, and then you got the 5 work days, and then the weekend. So let's play the longer, slightly longer one. Could not hear much on that. Yeah, so this one I think you can kind of hear it. It almost sounds like a car motor, and then I think you can hear it kind of decrease a little bit in its volume, which sounds like a decrease in pitch, but really I think it's just the amplitude decreasing. So that was kind of cool. And I don't have time probably to ask you guys, but I just wanted to point out, this is what the spectrogram looks like. It's really cool. So this peak here, the really bright one, is the 24 hours. So if you look at the true frequency, it's 1 over the number of seconds in a day. And it matches like perfectly. So that's the day, the 24-hour signal. And then as you can maybe see these other ones that pop up. And they're actually in increments of, they're in integer increments. So this one's at 50 hertz, 100, 150, 200, 250. And those are, yeah, I kind of wanted to hear what people thought they could be, but they're actually harmonics. And so whenever you have a really strong signal in your waveform, it'll show up with a harmonic that has all these other frequency components within it. And they're always integer numbers. So if your frequency is 100, then you'll have 200 and 300, and they kind of die out as you go further away. So I thought it was kind of cool that you could see it so clearly in this. And I will end by kind of showing this is the same data, but now I've gone back and taken data for every single minute for the past like 90 days or so. And it's a 50-second sound clip. So I'm just gonna play like a few seconds of it. This one, it's really hard to hear the difference after quarantine, but I thought I would just play it really quick. Okay. So I think you can hear just this daily kind of grind going on, like a kind of pulsating. And that's like the daily, that's like listening, sort of what I was thinking of it like is sort of listening to New York City, like breathing. You're sort of hearing the noise go up with people getting out, and then you're hearing it go down as people are going inside at night or sleeping. And you just kind of hear that over and over and over. And it's kind of an eerie thing to just sit there and listen to, but I thought it was kind of cool. And the spectrogram has a lot of really interesting stuff in it, but I don't know what a lot of it is. There's this line right here that's like 3 minutes, has a period of 3 minutes, so a frequency of 1 over whatever 3 minutes is in seconds, 180 seconds. And there are also these other lines. This one, it's really faint, and when I put my cursor over it, it covers it up. But that is about 10 minutes, and I was thinking maybe that could be the subway showing up, and it's showing up more after quarantine when a lot of the other stuff's not not happening. So maybe that's what that is. There are these other lines here that I'm not quite sure what they are, but yeah, this is, I just started looking at this today. So you're getting a fresh look, hot off the press, so.
Great, thanks, Josh. I'm also curious to see, you know, as things reopen, what this might look like. Can you talk a little bit about sort of where this, I think you mentioned this in part one with the resources in terms of where some of the data might have come from. But if any of our viewers are interested in kind of monitoring the sound levels, you know, what can they do and what can they kind of look up?
Yeah, so that is perfect for what I had next, which is I wanted, because somebody actually asked a question of how can you like access this data and look at it. And so I wanted to show people a tool really quickly called Station Monitor by Iris. And so you can actually, I have the website on my, on the resources section, but we can just go to it really quickly, iris.edu. And then Iris has a ton of really good education components. So there's this education tab and then Station Monitor, and they have a bunch of other stuff as well. This is like a really great, Iris is really great with their education outreach tools. Great. And it's just very quickly if this loads. So you can just put in, either you can find stations near you, or I'll do the Central Park one. So Central Park, New York. And then it actually loads the data in real time. So this is time on the y-axis, time of the day. So we'll actually go to yesterday. We'll go back in time and just look. This is what the noise actually looks like. This is what the data kind of looks like that I was processing. But you didn't see this version of it. You saw sort of what it looked like in the end. And the cool thing is they also have these notable events, so you can click and it'll actually take you to the seismogram that was recorded from that earthquake. And so this is in Central Park, measured this event in the Kuril Islands on March 25th. Oh, sorry, I guess we're looking, oh yeah, it is still the Kuril Islands, but, and there's a lot of cool stuff. It shows you in detail the first arriving wave. You can also listen to it, which I just found and thought was really cool. Maybe we could listen to it really quick.
Wow.
Yeah, so you can kind of hear there's a noisy stuff going on in the back, but yeah. So this is a really cool tool for anyone who's interested, and they also have an app for the iPhone and Android. Okay. And that was more or less where I was going to end it. So I'm happy to answer any questions or anything. I know we're
Great.
a little over.
Yeah, all good. Let's see if any of our participants have any additional questions. Someone did answer the question that you had asked about when you were talking about the Tohoku earthquake and the 3 different, and you played us the sounds of the 3 different stations, and asked us what those, I think what the vertical lines are. And someone had written that they, that the vertical lines might be beats. And there were sort of subtle differences. So yeah, I just wanted to make sure that that came back to you, and if you had any thoughts about that.
Yeah, that's a really good thought. So in this case, it turns out they're actually aftershocks. And the reason you can see them so clearly is because the station is so close to the earthquake. So you get the main shock. So you can see before the main shock, everything's kind of quiet. It's purple. And then as soon as you have the first earthquake, you start to get all this stuff going on. And then you get this aftershock here, you can see really clearly in the waveform because it's a big one. But then you can see all these other vertical lines, and those are all smaller magnitude aftershocks. And so that continued on for weeks and weeks and weeks, and yeah, and I mean, really small ones are still happening today from it, but.
Great, thank you for following up on that. Okay, so I don't see any additional questions, but let us know if you do, rewatch this and you end up with additional questions, I'm happy to send that information to Josh, and he'd be happy to take your questions. So Josh, anything else you would like to add before we wrap up?
Nope, I'll just leave it with this page for people who maybe want to go back and watch Genevieve's video or
Great.
watch the first part, but yeah, it sounds like people already kind of know where to find that.
Yeah, great. And we'll share a recording of this video along with the site that Josh has worked hard to put together all the resources on with everybody once this particular session has been edited and finalized. So with that, thank you so much again, Josh, for taking the time to do this. Very much appreciated. And I think it was super interesting. To be able to visualize the data and hear the data in different formats. And I think that's always great because, when you have data, you don't necessarily know what you're looking at, but if it's sort of translated into a different format, I think it's really helpful for, individuals like myself who are not sort of trained in science, but I can understand, I can digest that information in different formats. And so the sounds and the ways in which you've represented the information has been super helpful. So thank you for taking the time to do this.
Yeah, thanks for having me.
Great, of course. Yeah, and so thank you to our viewers for tuning in. And as I mentioned, we have these sessions going on until the end of June. So because next Monday is going to be Memorial Day, we will not have a session on that day. So we are going to be back on May 27th with a session about the Hudson River. So if you have any questions about our upcoming events, feel free to contact me or check out the Earth Institute, the EI Live website. So with that, have a great rest of the afternoon, and thank you again, Josh.
Thanks.